Now that we know that there are many coordinate systems, we want to learn how to perform all the basic tasks in polar coordinates that we learn to do in Cartesian coordinates. And one of them is graphing. So first of all, let's recall what graphing means exactly. So when we say, could you please graph the following equation, well, first of all, we do graph equations, and some equations are functions, so we also graph functions. But let's say if we have to graph this equation, then what does that mean? So that means that we have to, in the appropriate coordinate system, plot all the points whose coordinates satisfy the given equation. And when we do that, we produce what's called the graph of the equation. And the graph is made of points, and as a matter of fact, there are infinitely many points on every graph. And the one basic approach to graphing equations was taking a whole bunch of x values, and for each x value computing the y value, and then putting it all together in the form of an ordered pair, and those ordered pairs is what produced points on the graph. So this is your 0, 0, this is your 1, 1, this is your 2, 4, and so on. Now, what is going to happen in polar coordinates? Well, we're going to learn to do the same type of tasks, but what's going to happen is that now instead of having y as an expression in terms of x, we most likely are going to have r as an expression in form of theta. So for instance, if we take something simple like this, then immediately what comes to mind is that, hey, we're going to be, probably will be able to produce a table of inputs, outputs. So for different values of theta, such as, like let's say maybe 0, pi over 2, pi, 3 pi over 2, 2 pi, we'll be able to produce some values of r. So in this case it will be r is 0, this will be pi squared over 4, etc. And then each of these pairs will produce, each of these pairs of values will produce an ordered pair, which we then will be able to plot in polar coordinates. And by plotting this, we will be able to maybe figure out the graph. So in this case, maybe it's going to look something like this. Who knows, right? But whatever that is, we're going to call it a polar curve, or the graph in polar coordinates. So that's the rough idea. So now let's get into some details and let's discuss the grids. So what is the grid? Well, in Cartesian coordinate system, the grid is a collection of vertical and horizontal lines that we draw equally spaced according to the scale, maybe. So I'm just gonna, so let me highlight the axis. So axis will be in bold, and then the grid will be something like this, right? So we're gonna have line here, line here, line here. We're gonna have a line here. So again, I'm not gonna draw the full grid, but This is what a grid in Cartesian coordinate system looks like. And the question is, what would a grid in polar coordinate system look like? And to answer this question, let's first figure out what exactly are those lines that we use as a grid in the Cartesian coordinate system. Well, it turns out that those lines are the simplest curves or graphs of simplest equations in Cartesian coordinate system. So the y-axis, it's the equation, the graph of this equation. And I'm just going to label some of them. But this is as simple as it gets. So this is y equals 0, this is y equals 1, this is y equals 2, this is y equals 3. It doesn't get any simpler than this. So we may speculate, and we won't be wrong, probably, if we assume that the grid in polar coordinates will be the lines that can be described as theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2, theta equals 2 pi, or maybe r equals 0, r equals 1, r equals 2, r equals 3, r equals 4, and so on. So let's find out what the graphs of those simple lines look like. So let's consider the following equations. And let's graph r equals 1. What would the graph for r equals 1 look like? Well, the simplest approach we're going to take is we're going to take a bunch of theta. We're going to plug it in to the equation, and we're going to compute the output for different values of theta. And in this case, the way equation is set up, no matter what theta is, the r is always 1. Well, that should be easy to graph, right? So we're going to draw the polar curve, and we're going to graph the first point. The first point is 1, 0. So 1, 0 will be right here, actually. Right, so theta is 0, r is 1, so this is my first point. The second point is 1 comma pi over 2. It will be right here. The next point will be 1 comma pi, 1 comma 3 pi over 2, 1 comma 2 pi. And if you plot more points, you'll probably will recognize a circle. This is what the graph of r equals 1 look like. Now you can imagine that graphing r equals 2 is just as easy, except we're going to get instead of a bunch of 1s, we're going to get a bunch of 2s. So r equals 2 would look like a circle of radius 2, centered at the pole. Alright, that was easy. Now let's talk about graphing lines, like graphs of the following equations. So let's try theta equals pi over 3. So this time it doesn't matter what r is, theta will be pi over 3. So r could be 1, theta is pi over 3, r could be 2, theta is pi over 3, r could be 3, theta is still pi over 3, r could be negative 1, theta is still pi over 3. So how do you graph a collection of points like this? Well, pi over 3 is 60 degrees, so it's going to be facing that way. And at 1 we're going to get this point, if this is our scale. At 2 we're going to get this point, at 3 we're going to get this point, at negative 1 we're going to get this point. So you see that theta equals pi over 3 actually produces a line like this. That forms an angle pi over 3 with the x-axis. So similarly, you can graph theta equals 3 pi over 4. It will look something like this. It's just going to form an angle 3 pi over 4 with the x-axis right here. So this will be the graph of this line. Notice that the graph of pi over 3 will be the same exactly as the graph of negative 2 pi over 3. They would coincide, and the graph of 3 pi over 4 will be exactly the same as the graph of negative pi over 4. This is just by the nature of polar coordinate system. When multiple points can be written, the same point can be written in multiple ways. So going back over here, what would the grid in polar coordinates system look like? Well, it's going to be a collection of circles of different radii. So circle of radius 1, circle of radius 2. This is not the best grid, but circle of radius 3, and so on, and mixed with a collection of lines for different angles. So this will be pi over 2, this will be 0 and pi, this will be pi over 4, 3 pi over 4, or negative pi over 4, this will be pi over 3, this will be pi over 6, this will be 2 pi over 3, and this one will be 5 pi over 6, and so on. So if you've taken trigonometry, you should recognize this, all of these angles. But anyway, this is what the grid looks like. Now, having a grid actually makes graphing so much easier. So for example, if we consider the task of plotting the following points from the earlier lecture in the introduction to polar coordinates, you will find graphing much easier when the grid is provided. It's just much more accurate. Just like you need graphing paper to produce nice graph in Cartesian coordinate system, you do need nice grid in polar coordinate system to enjoy graphing in polar coordinate system. So let's plot these points real quick. 1, 3 pi over 4 will be right here. That's A. 2 comma pi over 6 will be right here. That's B. 2 comma negative pi over 3 will be right here. And negative 1 pi over 3, so we face pi over 3 right here, but we move negative 1, so in the direction of 4 pi over 3. So this will be the point D on this graph. So having this grid again makes it easy to graph the points or the curves in polar coordinate system. So let's go ahead and try graphing the following equation. So we're going to have let's say r equals 2 sine theta, and let's assume that theta goes from 0 to 2 pi. And we're going to graph it by producing a table of values for theta and r. And then we're going to produce those ordered pairs and plot them. So we're going to go with the standard values for theta. Let's go dense in the first quadrant. And then we'll loosen up a little. And let's compute. So sine of 0 is 0 times 2, 0. Sine of pi over 6 is 1/2 times 2, 1. Sine of pi over 4 is root 2 over 2. Sine of pi over 3 is root 3 over 2. Sine of pi over 2 is 1. 1 becomes 2. Sine of pi is 0. 3 pi over 2 is 3 pi over 2. Sine of 3 pi over 2 is -1, so it's going to be -2, and at 2 pi it's going to be 0 again. Interesting. So let's see what's going on here. We're going to plot all these points. So we're going to start with 0, 0, and then 1 comma pi over 6, square root of 2 comma pi over 4, square root of 3 comma pi over 3, 2 comma pi over 2, 0 comma pi. So we'll see how many points we actually need to plot to see the pattern, but the more the better. So let's go ahead and plot them one by one. So 0, 0 will be right here. 1 pi over 6 will be right here. Root 2 pi over 4. So root 2 is roughly 1.4. So at pi over 4 we're going to do 1.44. So something like around here. Actually, I'm not sure if it's 1.4, so let's go with, I'm not sure if it's 1.44, so I know it's around 1.4, so let's go right here. Right 3 is around 1.7 pi over 3, so we can call it here. Then we go to 2 at pi over 2, and then we go at pi, we're back to 0, so again, we may notice some symmetry here probably, and speculate that this will be the points. And at 3 pi over 2, so when we're facing 3 pi over 2, it's going to be -2, so we're going to be again here. So it seems like we're going to go this way, and then we're going to do another rotation. So we've seen this type of behavior in polar, not polar, but parametric, with parametric equations, when your curve is rather dynamic than static. So things like overlapping or a thing. And it seems like we're seeing the same type of behavior here. So it's not going to be unusual for us to see the curve to loop itself. And what does it look like, this shape? Believe it or not, it's a circle. Is there a way for us to kind of maybe convince ourselves that it's a circle, because it may not look like a circle to someone who's more critical? Let's see. One way that we can analyze the curves in polar coordinates is by looking at the equation and trying to figure out a pattern. And the tools that are available to us are the same tools that we used earlier to convert between the Cartesian and the polar coordinates. So these are the same four formulas that we get to play with to manipulate the equations to look a certain way. R is R, the radius, the radial coordinate. And in this particular case, we can do this little manipulation. We can multiply both sides of the equation by R. And if you do that, we recognize the R squared on the left and the R sine theta on the right. So we replace R squared with X squared plus Y squared, and we replace 2R sine theta with 2Y. Now we got rid of r and theta, and now we do a simple algebraic manipulation and complete the square by adding 1 to both sides of the equation. So we have x squared plus y minus 1 squared equals to 1 squared, and this is a circle. Again, we have more intuition in Cartesian coordinate system, so we do believe that this is a circle with radius 1 and center, and the center of this circle is at 0, 1. So in general, again, we can do this practice, but in general it should be easy to observe that any equation in the form r equals 2a sine theta will produce a circle of radius a and center and the center at 0, a. And the best way to graph the polar curves is the using Desmos. So let's take a look at what the graph of this looks like in Desmos. To graph this in Desmos, you will have to switch to switch the grid to polar coordinates, and to type the equation you simply use the same notation. So r equals 2 sine theta, and if you just spell out theta, it will turn that word into the symbol theta. So we see the circle of radius 1 centered at 0, 1. Now we can make this value a, add a slider, and you can see that as a gets bigger, the circle gets bigger. So, but it remains the circle. So guess what? If we replace sine for cosine theta, then take a moment to think about what do you think is going to happen. Well, because of the co-function identity, and cosine being the sine but of pi over 2 minus x, we're actually going to get the same kind of image, but with the whole image rotated 90 degrees. So instead of being centered on the y-axis, it will be centered on the x-axis, but the pattern is very similar. So we can also conclude that a circle, the equation 2b cosine theta will produce a circle, but the circle will have the radius b and center at b, 0. So it's very easy to verify doing the same steps that we did earlier. So let's try another problem, and let's convert the following equation. Let's try to analyze this equation but without graphing it, without doing all that, creating all the table of inputs and outputs. So one way we can analyze this is, again, here's our tools. We don't really have many tools, but we can manipulate the equation using these tools and turn it or reshape it into something recognizable. So one thing that we can do here is, it seems like we can benefit from multiplying both sides by r. And what do we see? On the left side we have x squared plus y squared. On the right side we have 2x plus 5y. So it looks like it's some circle, but shifted somewhere. Where exactly it's shifted we can figure out by completing the square. So I'm just going to do it real quick just for the sake of completion, but keep in mind this is just algebra. So I would add 1 over here to complete this square, and I would add half of 5 squared, which is 25 over 4, to complete this square. And now, after completing the square, we get x minus 1 squared plus y minus half of 5 squared. All that equals 29 over 4. So what is this? This is a circle of radius square root of 29 over 2, and the center 1,5 over 2. So we were able to analyze the graph of this equation given to us in polar coordinates without actually going through all that input-output calculations. So let's input this in here. So we have 2 cosine theta plus 5 sine theta. And does it look like we have a circle centered at 1,5 over 2? Yeah, so this appears to be the center, and the radius, I would assume it's square root of 29 over 2. So again, when working with polar coordinates or in polar coordinates, you can always try to change the equation and rewrite it in Cartesian form. However, going backwards is actually easier. So if we take the following example, and it doesn't matter and it doesn't matter what type of equation you have, as long as you have it in Cartesian form using like x and y. So it could be very complicated. Remember, the tools that we have allow us to use these two formulas and rewrite any x or any y using the r and theta. So I would rewrite this equation by literally replacing x with r cosine theta, y with r sine theta, missing the squares, and do it everywhere, right? So we're gonna get 6 times r cosine theta plus 3r sine theta, and after reduction we get rid of r, so the only r we have is on the left side, and we can factor it out, and we have 6 cosine theta plus 3 sine theta, all that divided by 2 cosine squared theta plus 2 sine squared theta. But that's Pythagorean identity, so we can reduce it further and rewrite it as 3 cosine theta plus 3/2 sine theta, which is the final answer. So again, going from polar to Cartesian can be difficult. Going back, it's pretty straightforward. So when you graph, consider just using a graphing device, or analytically you can analyze the graph by trying to convert it into something that you are more familiar with. So we're going to end this section with a brief summary of what we consider standard curves in polar coordinate system. So anything that looks like this, or a sum of the two, will be some circle. Anything that looks like this, so a number plus minus b sine theta, or a number plus minus b cosine theta. So the graph of this will depend on the relation between the a's and b's. So if the two are the same in the absolute value, then you're going to end up with a shape called cardioid. If a is greater than b, then you're going to end up with a shape that there's nothing special. So I call it meh curve. It's like, what curve did you get? It's a meh curve. It's like, doesn't look like anything special going on there. And if a is less than b, we're going to end up with the curve that it's called limaçon or limacon. Not sure. C. Limaçon. Now, when you start throwing things inside, like notice how we have theta multiplied by n, things will be happening at a faster pace. So that will create what's called a rows. And the number of petals in the rows will depend on whether n is even or odd. So if n is even, you're going to get twice as many petals. And if n is odd, you're going to get exactly that many petals. And the last shape is, I would like to mention, is something that we consider to be a very simple equation in Cartesian coordinate system, like the linear mx plus b. In polar coordinates creates something interesting that we call a spiral. So it's definitely not an easy line. So curves in polar coordinates, the ones that have nice equations in polar coordinates may not have nice equations in Cartesian coordinate system, and vice versa. So what used to be a nice straight line y equals mx plus b doesn't have a nice form in polar coordinates. But here's, let me show you the difference between the cardioid and meh curve and limaçon. So when a equals b in absolute value, so it doesn't matter, a could be b or negative b, you're going to get a cardioid. When the absolute value of a is greater than the absolute value of b, you're going to get like this type of shape. Meh curve sounds pretty much appropriate. And when a is going to be less than b, you're going to get this interesting behavior right here. You're going to get a loop inside of the loop. So, and this is what we call a limacon. Now for roses, it's going to be something like this. Here the n corresponds for the number of petals. When it's a fraction, you get some, when it's a rational number, you get some, you may get like some crazy picture. But if we just make n integers, and let's start at 1, then you see how for n equals 3 we have 3 petals. For n equals 4 we have 8 petals. And a is corresponding for the stretch factor. Alright, so this was the introduction to graphing in polar coordinates.